So this is the CHEM14. That's not right at all. It's not a complete bad start. This is the CHEM4 June 14 paper as a run through, which I'm doing in preparation for the CHEM4 exam tomorrow, or in a different year. If you're listening to this in a different year, different day, I know. I'm missing Game of Thrones for this, so I hope that's shows my dedication. So anyway, Unit 4, organic. Calculation bits, all that usual sort of jazz. I'm going to whiz through. I'm hoping to do it reasonably quickly. I'm not going to mess around. Get rid of that. Something like hour and 10 would be nice. It'd be delightful, in fact, but we'll see. So, usual like bits on the front, 100 marks, all that stuff. In we go. I've done it again. This weird thing. Don't know what it does this for. There's supposed to be an equilibrium there. Anyway, yours should have that. So EFG gas equilibrium between these two compounds. So 2 mole sample of E was heated in a sealed container with 1 mole sample F. Equilibrium was established at a given temperature and the equilibrium mixture formed contained 0.8 moles of G. So we've formed, so I tend to think of these in two halves. We've got initial and then we've got at equilibrium. So we know that initially here, not a lot of room there, we had 2 mole of this and we had 1 mole of this. But we know at equilibrium 0.8 moles of this was formed. So we know the reaction is 1 to 1, which means for 0.8 of this to be formed, 0.8 of this must have been reacted for this to be 1 to 1, which means there must be 0.2 of this left. So 0.2 left of F. E, what do we got here? So we start with that ratio of 2 to 1, which means to form 0.8, 0.4 must have reacted. Because there was initially 2, we must have 1.6 at equilibrium. So first one there, 2 reasonably straightforward marks. Write an expression for the equilibrium constant Kc for this equilibrium. So Kc, products over reactants. So bear in mind we've got the 2 there. So we're going to have concentration, got to have your square brackets there. G, and then we had, it was E, wasn't it, and F, 2F, so again squared. Nice, straightforward, another easy mark there. Units, well, what I would do here is I would actually write the units out. It's quite a nice one, I think, to get your head around, to get you started doing it. And I'll do it on this one, although it's actually quite an easy one, this one to go, but there we go. So the units would be mole per decimeter cubed multiplied by mole per decimeter cubed over mole per decimeter cubed mole per decimeter cubed mole per decimeter cubed. That cancels with that and that, which basically leaves you with 1 over that. So units are going to be mole to the minus 1 dm to the plus 3. If you want to put your plus, you can do. Just leave it as the 3. Make sure you don't put a negative there, though. That's the fairly key thing, and that's because it's 1 over that. Mathematically, that's how it works. 1c, a different mixture of E and F reached equilibrium at temperature T1 in a container of volume 1.5 decimeter cubed. This equilibrium mixture contained 2.5 moles of E, 1.2 moles of F, and 0.85 moles of G. So they're giving you the equilibrium values, which is spot on, but it's the same reaction there, so it's still, I would rewrite that, it's still going to be G squared E F squared. Key thing is here, note these are concentrations, therefore we've got to do moles over volume. Key thing there, although when it comes to the calculation, do we need? Yeah, you need to do it because it's gonna tie into particularly the way this works, because it's not an even one. Yeah, get into the habit of putting your volumes in there. So values given, we're gonna have 0.85 divided by 1.5. That's our volume there. Nice one. That's containing the overall volume there. So that's a nice one there. Square that. We're gonna have it over 2.5 divided by 1.5, not squared but multiplied by 1.2 over 1.5, all squared. Boom. And that's going to give us an answer of 0.301. 2 more marks there. Nice. It's not requiring units for this one, but obviously we wanted units. It's going to be the same thing as before, mol to the -1, dm3. So it might be worthwhile sticking them in there, although the mark scheme does say ignore units, because you can't lose the mark twice for the same thing. It's a little bit harsh. Even AQA aren't that bad. The mixture in question 1C was allowed to reach equilibrium at temperature T1 in a different container, volume 3 decimeters cubed. State whether the amount of G in the equilibrium mixture will increase, decrease, or stay the same. Explain your answer. So it's allowed to reach equilibrium at a bigger in a bigger container, so it has a greater volume, which means therefore the pressure is going to decrease. Pressure decrease. Let's go up straight up to G. It's this thing here. Pressure's decreased. It's going to move to the side which has the greatest number of moles. Here we have 3 moles. Here we have 2. So it's going to shift in that direction. So G is going to decrease. Do keep referring back to questions. Just because it's 1D doesn't mean it's not changed from that 1, which is all about that equilibrium there. So do turn back. Don't just ignore it. So the amount of G is going to decrease. Explanation. Well, I'd probably go more moles on left hand side. Therefore, love a good therefore symbol. Position of equilibrium shifts left, and I'd probably throw in to oppose, because they always love that. It's not worth marking this one. To oppose, decrease in pressure. That's going to get you 3 tasty little marks there, which is at this point nice easy introduction to the paper. You're more than likely going to get equilibrium as your starting question, or certainly one of the first questions, along with acids and bases and kinetics. They'll more than likely come at the start. Occasionally they throw it out there and they put one at the end. Generally speaking, you're going to get them at the start. 1E, it's 12 marks total for this question. 1E, the mixture in question 1C was allowed to reach equilibrium at temperature T2 in the original container of volume 1.5 decimeters cubed. The value of Kc of the equilibrium was found to have increased. State and explain which of T1 or T2 is the higher temperature. So, let's have a look at this equation again. Right, so I had a good look at that. I'm going to go with this one. Higher temperature is going to be T1. And the way to work this out is to look back at the... If we know that Kc is going to increase, and this all relies on you really having the correct equilibrium expression, but if Kc is going to increase, ultimately we've got to increase this number. This has got to get bigger. Okay, all these have got to get smaller. Either of those is true. But this has got to get bigger, these have got to get smaller. Well, looking back at the equilibrium, how can that happen? Well, if we shift the equilibrium to that direction, we will decrease these and increase these. So we're looking for it to shift to the right, okay, in order to allow us to increase the value of Kc. Well, this is an exothermic reaction. To shift it that way, we've got to drop the temperature. So, back to here. So T2 increased the Kc, which meant it must have been at a low temperature to favour that forward exothermic reaction. Therefore, T1 must be higher by the same reason. So the explanation, forward reaction is exothermic. So it's your standard answer really here. Therefore, equilibrium position shifted to the right to oppose the reduction in this case in temperature, and that's reduction because of that old guy there, T2, sneaky. Okay, question 1 done. How many questions have we got? 8. Oh, got 8 in total. So that's question 1 done. Let's crack on to question 2. Question is about alkalis and carboxylic acids. Okay, I can see where this is one's going to probably go at some point. I'm thinking a buffer. This question is about alkalis and carboxylic. All data quote weak acids. State the meaning of the term weak. So weak, partially dissociated. You can say ionized. I prefer the term dissociated. Boom, done. Write an equation for the reaction of propanoic acid with sodium carbonate. Standard equation. You should be able to do this. Probably year 9s could probably push this one out. Maybe. So, sorry, I'm in a tangle with my wires. Doing my head in all over the place. Equation, sorry, sodium carbonate. So I'll write sodium carbonate first. Obviously you need to know that it's Na2CO3 or you're not going to get your marks. Propanoic acid, CH3, CH2, COOH, my 3 carbons there. What are we going to produce? We're going to produce a salt, we're going to lose the H, we're going to add the Na, so we're going to go CH3, CH2, COO, Na, and we're going to add on to that water, because it's a carbonate reaction, and carbon dioxide. We're going to have to double this up, because we've got 1 Na there, we've got 2 there, and we're going to have to double this up to balance. It should be fine. Do it ionically if you want. I wouldn't bother. I think you're just treading on thin ice there. Don't go for it. Stick with that. Okay, pH of a 0.0120 mole per decimeter cube solution of calcium hydroxide. Sneaky. Giving you a kW value there as well. So, calculating the pH, so we ultimately need to find the H plus value because it's a pH calculation. Calcium hydroxide, don't get tricked out by this one. Calcium hydroxide is CaOH2, which means when it dissociates like that, which does it completely because it's a strong alkali, strong base, you're going to actually get it doing this. Okay, and that's really, really key because that's going to change the values massively. 0.0120 concentration of this one means this one's going to be 0.0240. Oh, that's going to get you a mark, that initial calculation, the fact that you've multiplied this by 2 to get the concentration of the hydroxide ions. Then from that point it's usual stuff, so we've got Kw equals H plus multiplied by OH minus. Rearrange that because we want to find H plus, therefore H plus, and always rearrange your questions. OH minus, stick your values in, 1 times 10 to the minus 14, voice is going croaky, 0.0240, so whack those numbers in, boom, 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 and we're come out with a value of 4.166 times 10 to the minus 13. Obviously, we've got to logarify it, so pH being the minus log of the H plus. Notice I'm writing everything out. I'm just going to do that here. Our answer is going to be 12.38. Please read the fact that it's to 2 decimal places, okay? 2 decimal places, 12.38. It's a fairly nice calculation. You're going to trip up though because you're going to forget to do the double in there, and that's going to cost you. You're not going to lose everything there. If you've missed that, you're still going to score a couple of marks. I'm trying to think what you can get. You can still score 1 mark out of 3 if you haven't doubled that. So it's, you know, it's not the end of the world really. Right, let's continue. Write an expression of the acid dissociation constant Ka for benzene carboxylic acid, this guy here. So we've got Ka, products as before. Might be worth writing the equation out if you're a bit unsure. So C6H5COOH. Obviously we've got carboxylic acid, so we've got partial stuff here, and that's why we're writing down our expression. So top row here, as with the equilibrium stuff, it's your products first. What is the obsession with writing 3? I have no idea what I'm doing here. This is absolutely appalling. Right, let's change this because that is just shocking. What are you doing to yourself here? Get a grip of yourself, man. C6H5CO, yeah. And then here again. C6H5. See, I'm rushing and stressing. COO minus H plus C6H5COOH square brackets. No calculation required. Just thinking the expression down, 1 mark. Key point. Calculate the pH from 0.0. Well, a bit more room here, I like that. 0.0120 mole per decimeter cube solution of benzene carboxylic acid. I would write down. I would stick with as it is before. And I forget what it was now. It was C6H5COO minus. Now at that time, multiplied by H plus, and then at the bottom it was C6H5COOH. So, how to work this out? Basically, because we know that quick bit of theory on this one, because we know that it's going to dissociate in a one-to-one ratio, we know actually the concentrations of these two guys are going to be equal. So, we can rewrite this as this. COH. Now, we're given a concentration for this. Now, the other assumption you can make is always the same thing. Assume that, obviously, it's a one-to-one ratio, because it is. The other assumption is that none of this has actually, because it's carboxylic acid and it's the dissociation is so minimal, you basically have to assume that none has dissociated of the carboxylic acid. Now, whilst that's not true, it certainly gives you a starting point and allows you to actually calculate the stuff. So we're going to find Ka is going to be equal to unknown squared over 0.0120. Now I'm going to rearrange this as H plus, because I think it's always a good step to do that. We're given our Ka up here, so let's stick this. H plus squared is going to be equal to Ka multiplied by C6H5COOH there, which is going to be equal to 6.31 times 10 to the minus 5, just getting that around there. 6.31 times 10 to the minus 5. Just checking I've rearranged that correctly. I think I have, haven't I? Yeah. Multiplied by 0.0120. Obviously, if you want to just work out the H plus, it's going to be that value square rooted. pH then is going to be the minus log of that value, which I'm not going to go through all the workings out. You can do that fairly straightforward. And I think this actually comes out to something like 8.70 times 10 to the minus 4. pHify it, and we're going to get a pH of 3.06. Again, 2 decimal places. You don't put your 2 decimal places, you're kissing goodbye to that third mark, which is just a really stupid thing to do. Nice, relatively easy sort of calculation there. If you get your head around the acids and bases, you're going to pick up a huge number of marks, and here it is, buffer. I knew a buffer was coming. Oh, we've still got another question after this as well. Oh, look at this. Calculate the mass. It's a different buffer one. So a buffer solution with a pH of 4 is made using benzene carboxylic acid and sodium benzene carboxylate. Calculate the mass of sodium benzene carboxylate, the MR of 144, that should be dissolved in 1 decimeter cube of 0.0120 mole decimeter cube solution of benzene carboxylic acid to produce a buffer with a pH of 4. The value of this acid dissociation constant Ka is this. Right. So that is a very different calculation. I'm trying to get my head around where I'm going to start with that. So I'm probably going to start by writing my Ka out. That makes me feel comfortable. So usual things before CH3CO CH. What is the obsession with that? C6H5CO minus H plus, concentrations of both, divided by C6H5COO minus. So that's my starting place there. Now, right, so we're given a pH this time. This is the confusing thing. We're going to have to work out the H plus. Now, H plus concentration we can work out by saying it's 10 to the power of minus pH. In this case, 10 to the power of minus 4, which is 1 times 10 to the minus 4, which is fairly useful. That we can feed directly into there. Bit of rearranging here, and what are we trying to work out there? So we're trying to work out this guy, the concentration of this. So let's rearrange. Let's say that our C6H5COO minus is equal to Ka multiplied by C6H5COOH, that is a CO, divided by H plus, which of course we have a value for now. Let's feed some values into that. Let's put our Ka in. We've got it given again there, same value as before. 6.31 times 10 to the minus 5 multiplied by acid concentration 0.0120 divided by 1 times 10 to the minus 4 my H plus concentration. Boom, that's going to give us an answer of 7.572 times 10 to the minus 3. At this point here, we've worked out the concentration of essentially these guys, which is the benzene carboxylate ion, so the salt ion there. So we've worked out the concentration of that. We need to convert it to a mass. So moles is concentration over volume. Let's rearrange that. Let's go for in fact, do you even need to do that? No, you don't. This is in moles per decimeter cubed. We can convert that mole directly into mass. Silly. Ignore that. That was a schoolboy error just made there. So moles is mass over mR. We've given our mole. We want to work out mass. So mass is mR times moles. Well, because it's per decimeter cubed, we can ignore that for now and just say that we've got 7.572 times 10 to the minus 3 moles per decimeter cubed, but it's the moles that we're after. So let's convert that. So let's do the mass of the C6H5COO minus, and that's going to be 7.572 times 10 to the minus 3 times the MR, which I believe was 144 back from the question, and that's going to give us 1.09 grams. So it's a very much a twist on the usual buffer calculation. They're not getting to work out the pH of the buffer. They're asking you to work it backwards and really show an understanding of what happens. It's only question 2, but they're going for it. Really show an understanding of sort of of how the buffers work, and then working backwards really. But still, it's still a fair question to get, and actually not too bad for 5 marks. There's a lot of sort of real good marking points there, and if you know your buffers, you will be able to work that out. It's different. Break it down. Start with what you know, and work it out from there. Okay, 2 solutions. One with a pH of 4, the other with a pH of 9 were left open to the air. The pH of the pH 9 solution changed more than that of the other solution. Suggest what substance might be present in the air to cause the pH to change. Explain how and why the pH of the pH 9 solution changes. The word pH, look at it. Once, 2, 3, 4, 5, 6, 7 times. Ridiculous. I might have missed one as well. Who knows? So, substance present in air. I'm thinking ordinary air. We're talking about carboxylic acid. Forms a weak sort of alkali solution. I found out the other day that fizzy water, sparkling water, which I love, is actually a bit acidic and can actually damage your teeth. But I don't care. I'm going to keep drinking it. Explanation. So what happens? Well, what are we dealing with? What pH? So this one, the one with constant on. It's the pH 9 solution. So pH 9 means it's alkali. So the CO2 reacts with alkaline solution. Specifically, obviously, the OH minus ions. What does that cause happen? Well, that causes obviously the pH ultimately is going to fall. And that's actually it as a question. There's a lot of there for actually what is quite a simple question. I'm talking 17 marks now, so about 29 marks into the paper. About a third into the paper in the first 2 questions, so we know it's going to hopefully get a little bit quicker as we go through sort of shorter marks. But there you go, bish bash bosh. Question 3. So kinetics. 3H. Table 1 shows the results of 3 experiments to investigate the rate of reaction between compounds A and B dissolved in given solvent. All 3 experiments were carried out at the same temperature. Excellent. So we're asked, reaction with respect to A, is it 0 order, 1st order, or 2nd order? They've given the results in an awkward thing. They don't normally do this. They normally the other way around. These would be down. But there we go. Not a big problem. Okay, let's look at this one here. So if we look at B, which remains constant, so B is not changing, but we can see that the initial rate is changing, therefore we know that A does affect our rate of reaction. Now A goes up by 1.5 times. A goes up by 1.5. Does this go up by 1.5? No, it doesn't, but so it's not a first order reaction, but if I do 1.5 times 1.5, it gives us 2.25. That's 1.5 squared. 1.8 times 2.25, 4.05. So what's happened, what we can tell from that is that the change in A, the change in concentration of A, whatever that change is, has been squared, meaning it's a second order reaction with respect to A. Let's have a look at B now. Right, so good. I like when they do this. Lovely of them. Thanks very much. Okay, so we've got no simple one. A doesn't stay the same like it did, like B stayed the same here, and we can compare them. We don't get that for A. So let's have a look anyway and see what happens. We're going to look at B, but because we know that A is second order, okay, we're going to see what happens to the rate according to A and see if B is changing the rate at all, because B could be zero order. So the rate in this situation here, well, let's have a look at here. 1.6 times 10 to the minus 2 is 2.4 is again, I believe, 1.5, isn't it? So we're looking for again an increase of 2.25. Let's have a look. 8, again this is times 10 to the minus 5, remember, times 2.25, nailed it, 18, that's what we want, times 10 to the minus 4. So actually it has gone up by a squared multiplication factor that it has there. So B has, although B has changed, it's had no effect, therefore B is zero order. Nice, 2 marks. Quite a bit of work there for 2 marks, actually. They do make you work for it. Calculation, not too bad here. So blah 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 blah, blah. Compound C and D, given temperature, rate equation of the reaction is found to be rate equals K, the concentration of C, concentration of D squared. When the initial concentration of C is 4.55 times 10 to the minus 2, concentration is D, initial rate. So we're asked to calculate the rate constant. So I would probably go straight into rearranging this here. You got it up there. Rate at K is equal to rate over C multiplied by D squared. Am I right with that? Yeah, I am, yeah. The rate is given as 6.64 times 10 to the minus 5. C is given, don't forget the square there, important. C is given as 4.55 times 10 to the minus 2. D is given as 1.70 times 10 to the minus 2. And of course we're going to square that value there. And it's going to give us 5.05. Units wise, I'll show the unit calculation down here. We'll do it here. So rate, units are always mole decimeter cubed per second, and I'm getting that from over there. That's going to be on the top line. The bottom line is going to be concentration times concentration times concentration. So mole per decimeter cubed multiplied by mole per decimeter cubed multiplied by mole decimeter cubed. Bam, cancel. So it's basically 1, or s to the minus 1 over these two. So we're going to reverse the sign. So it's going to be still squaring them. Mole squared, it's going to be mole to the minus 2. dm, rule of indices, you add them when you multiply. So it's going to be dm, but to the positive 6, because it's 1 over them, still seconds to the minus 1. So mole minus 2, dm plus 6, and s to the minus 1. 3 nice little marks. Okay, experiment question 3bi is repeated at the same temperature, but after the addition of extra solvents, the total volume of the mixture is doubled. Right, so if we double the total volume here, we're going to halve the concentration at each point. So basically, what I would do is I'd just rework this one out with halved values here, halved values here. The trick, though, is each 1.7 here is going to be halved. So it's got to be 4.55 times 10 to the minus 2 divided by 2 times 1.7 times 10 to the minus 2 divided by 2 times 1.7 times 10 to the minus 2 divided by 2. Don't just halve 1.7 times 10 to the minus 2 squared. It's got to be halved of each of the calculation points there. That's going to give you a value of 8.3 times 10 to the minus 6. Units not required. because that's obviously the rate that we're looking at there, so units not required. Do bear in mind, and actually I did that quite sloppy job there, you've got to obviously put it into this usual, you've got to put it back into this form, don't put it into there, that's a bit bad of me there. Do put it back into rate equals K, CD, like that, okay, and then work it out as, again, just the halved concentrations. 1 mark, only 6 marks now, so we dropped there. But again, as I said, first 3 questions: equilibria, acids and bases, and kinetics. So we've still got all the organic to come, organic synthesis, spectroscopy, all that stuff to come as well, and polymers, of course. Here we go. Name the strongest type of interaction between polymer chains of Kevlar. Kevlar, I've got nitrogen and hydrogen there, therefore I've got hydrogen bonding. Lovely job. 1 mark. Nice. One of the monomers used in the synthesis of Kevlar is this guy here. An industrial synthesis monomer uses the following 2-stage process starting from compound X. So, suggest why the reaction of ammonia with X in stage 1 might be considered unexpected. This is one of those suggest questions, and the problem with these is it's sort of like, what do you think? It's based on your chemical knowledge, and it's really pushing sort of a real in-depth sort of understanding of how chemistry works is really what they're looking for there. So you're not going to get the answer to this one just out of a textbook. You are going to have to use your brain a little bit, but it's not the end of the world. If you think back to sort of nucleophiles, because that's what we've really got happening here. We've got ammonia is going to attack this, and ultimately it's this part here. It's the chlorine here where we've got this delta positive region, delta negative region. That's where we'd expect the ammonia to attack, as it is going to. But look at this, we've got this huge area of electron density there. So what we'd normally expect is that ammonia to be repelled as it is a nucleophile. And the other way of sort of, when I teach this nucleophile, the idea of sort of loving positivity, you know, it's attracted to that positivity. So ammonia is to be repelled as it is a nucleophile. I'll do that. Ammonia is to be repelled by benzene as it, being ammonia there, is a nucleophile. So that's what I'd go with in that. Suggest, a bit of a horrible question, but, you know, deal with it. Suggest a combination of reagents for the reaction in stage 2. So we're going from the nitrobenzene to an amine. So that one there, basically the 2 options are, the one I think I always teach is SN, so tin and hydrochloric acid. A couple of other options as well. Hydrogen with a nickel catalyst is, I think, the alternative that I normally teach. I forget now. I always forget that one though. It's one of those that sort of sneaks under the radar, I find. Compound X, so compound X is this one. So it's the chloro-nitro malarkey. Can be produced by the nitration of chlorobenzene. Right, so on to nitration now. It's aromatic stuff. Give the combination of reagents for this nitration of chlorobenzene. Good. So reagents to nitrate something. We've got concentrated nitric acid. And we've got concentrated, must both be concentrated, sulfuric acid. And the equation that occurs here, it's the H2SO4 reacting with HNO3, and there's a couple of ways of writing this. This is how I write it personally. We form the nitronium ion, I do the hydrogen sulfate ion, and water. The reason being there is there's no balancing required, and I just think it's a nice straightforward one. It's going to score you 3 marks, 2 for the top one, 1 for the bottom. Right, name and outline a mechanism. The formation of X. So X was this chloronitrobenzene, or chloronitrobenzene. So what's the name of the mechanism? Well, it's involved in the acylation there, so it's electrophilic. We know it's electrophilic because, well, generally speaking, it's involved in the benzene. Be careful, they do sometimes put application ones that involve benzene as well, but generally speaking, electrophilic. And it's substitution, we deal with the A2. Mechanism. So it's important on this one to realise that chlorine is already bound, okay, and because it's coming, we're basically forming it, the nitrochlorobenzene or chloronitrobenzene from chlorobenzene. So, and we've got to get in the right position as well. The chlorine was opposite the nitro group. So there's my benzene ring, there's my chlorine. So my attack's going to occur so that my nitro group gets added on here. Usual lark here. Put the positive on the nitrogen. that's the electron's going to move on to there. It's going to be your first mark. That's going to lead us into this next portion here. Probably could have made that a little bit bigger. Make sure you've got this correct shape there. Hydrogen and the nitro group bound, and then the hydrogen electrons come from the bond and move in there. You can make sure this horseshoe is centered around this carbon here. They are very, very much on there. If it's all wonky, just like my horrible benzene, like that, then you would lose the marks. It's got to be centered around that carbon where the substitution is taking place. And that's actually the marks there. You've got 4 marks, one for that, one there, and one for the shape. 4 marks. That's 11 marks in. Boom. Question 5 of 8. The carbonyl compound CH3, CH2, CHO reacts very slowly with hydrogen cyanide. Name and outline a mechanism for the reaction of CH3, CH2, CHO, so this is our aldehyde, with hydrogen cyanide. Don't get confused with this being the nucleophilic addition elimination. It's just nucleophilic addition forming the hydroxynitrile in this case, because it's the CN- that's going to do the attacking. So we've got CH3, CH2, CHO, always written in that way round, not COH. We don't want to think that it's an alcohol group, not at all. Our first step then is going to be the cyanide group. We do get it correct. It's a nucleophile, got this lone pair of electrons. The negative is on the C. They will actually, I believe, penalise. No, they will let you have the negative on the nitrogen, but it strictly speaking is on the carbon there. So that's moving forward. Probably better to have it moving a little bit further forward actually than I have done there. Obviously from the lone pair right onto there. Movement there of electrons. We have our next stage going on, which is, I'll abbreviate the first bit, CH3, CH2. We now have, I don't want that there actually, it makes it a bit of a nightmare for drawing the next bit. Put the H there. CN is now bound, and then we're going to go like this to our H plus, and we're going to get a little bond occurring there, which is ultimately going to form us our final product, okay, which I don't believe we need to draw in this case. No, we don't. But if it would just basically be same thing there with the CN, OH, H, blah, 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 there. So the hydroxynitrile, bear in mind it starts there. So key points there, obviously we finish off with that bit there, and we have the charge as is correct there. 5 marks, 1 mark there, 2, 3, 4 for the structure, 5 for the arrow there. Okay. The reaction in question 5a produces a pair of enantiomers. Draw the structure of each enantiomer to show how they're related to each other. So we're looking for this one, the enantiomer. Right. So probably worthwhile drawing out what you've actually got. So we've got CH3, CH2. Work out what we're dealing with. We've got the OH there, we had an H, and we had the CN. So it fits the, obviously it does, given the question, chiral carbon, this one here, 4 different groups attached. Draw it out. I think the best thing to do, stick with it as roughly in the sort of similar order here. I like to use the shapes on the arrows, although you aren't required to. The mark scheme just has ordinary sort of arrow, lines, but I quite like it. You are best, and this is, I'm now trying to think of how I'm going to do this. It's not really ideal, but there we go. Written that backwards. It probably would have been better to have done that in a better order, or switch it around somewhere. But there we go. I'm trying to think if they'll let you have CH3, CH2. Schoolboy mistakes on this one. So you've got to concentrate, kids. Concentrate. I think you are allowed to actually write it as CH3, CH2. If you don't want to, then H3C, H2C is the better way around, but I'd probably stick with that, you'll be alright. Mirror image, it's a direct mirror image, that's the key thing here. CN, something like that, boom. That needs to look like that. And there you go, 2 more marks. So the correct structure, obviously, and then the correct mirror image from that. So ignore my silly mistake I made just then. State and explain how you can distinguish between the two enantiomers. Really nice question. So, plain polarized light would be rotated in opposite directions by equal amounts. That's got the idea of opposite rotation there. So one 90 degrees, the other 90 degrees. Product in the reaction of question 5a, so it's this guy here. What's it called? Don't mess up with your initial starting point there. So it's 1, 2, 3, 4. Nice bit of nomenclature. So it's bute as its backbone. It's a nitrile. We've got a hydroxy group on the second carbon, so it's going to be 2-hydroxy butane nitrile. Butane nitrile. 1 mark. In practice, KCN rather than HCN is added to the carbonyl compound, given that Ka for HCN. It's just why the reaction with HCN is very slow. Well, we're given a Ka, so we know that this therefore is weak. If it's weak, it means that HCN only partially dissociated. And bear in mind, it's not the HCN that we're reacting to, it's the Cn minus ion. Therefore, Cn minus concentration is low. So what I've done is I've taken that concept of, you know, the weak, the partial dissociation, and then linked the idea of actually it gives us a low concentration of cyanide ions. That's the key second point that you must have there. Oh, this is still going. Acrylic fibers are used to substitute for wool. Acrylics are copolymers of acrylonitrile and with other compounds. Acrylonitrile is a common name for the following compound. Acrylonitrile can be formed from propene. Write an equation of the reaction of propane with ammonia and oxygen. Right, okay. NH3. I don't know why I've done it that way around, but there we go. And propene. So they're quite keen on you putting the double bonds in on this one. You can do it as C3H6. I think it's always nice to show where the double bonds are. CH3. And that's going to produce this guy, but obviously we're going to have to get something else that get rid of it as well, which is going to produce water in this case. The one other product, you've got to work that one out really. H2C CHCN plus water. Balancing it up, what do we got? 1 NH3 there. So it's just the oxygen that's not balanced, isn't it? So oh no, hold on a minute. 3, 4, 5, 6. Yeah, so we have to triple that one. 3 oxygens, so 1.5 there. 1.5, 1.5. Balanced up nice and neatly. Or you can double it. You can have the doubled one. I don't know if they'll go for all sorts of multiples, but you can go doubled. Okay, two-term copolymers used to describe the product obtained when 2 or more different monomers form a polymer. Draw the repeating unit of the acrylic copolymer that contains 75% acrylonitrile monomer and 25% chloroethene monomer. Right, so go back up to here, and whilst this looks very confusing on sort of on the surface, it's actually no different to any sort of other monomer. Base it around the double bond, so it's going to look just like this. So that's what it's going to happen. That double bond's going to break. It's going to make the other thing. So it contains 25% acrylonitrile to 25%. So 75 to 25 is 3 to 1, the ratio. So 3 to 1 of that one. So let's put 3 of these in. So it was, what was up there? It was just the, yeah, so I think I had that down there. 1, 2, 3. We know we're going to have 4 because it's going to be the other thing. It's reacting, so it's formed with 75 then 25% chloroethene. And a CN, and then finally 8, and then a Cl. So I've met that ratio. I don't need to put the brackets round. The trailing bonds are required. You've got to have that because that's the repeating unit. You must have trailing bonds. But the brackets and the ends and things you don't need because you're not writing an equation. You're just writing the repeating unit. What type of polymerization is this? It's addition because it's dealing with the alkenes being added to each other. So 15 marks there. So quite a nice scoring one again. And I think quite a nice polymers question. They're sometimes a bit mean, but I think that one's actually quite a good one. Oh, amino acids. UPAC name of lysine. So lysine alanine, UPAC name of lysine. So what have we got here? Always base it around the fact that it's a carboxylic acid. So 1, 2, 3, 4. God, what a horrible thing. 1, 2, 3, 4, 5, 6 carbon. So it's going to be a hex. It's going to be 1, and then on the 6, so it's going to be 1, 2. It's a hexanoic acid. These are amino groups, so it's going to be diamino because there's 2 of them. And we've got to position them, so 2, 6, diamino hexanoic acid. Nice. Draw structures show the product formed in each case when lysine reacts with an excess of aqueous hydrogen chloride, so hydrochloric acid, hydrogen chloride, whatever. So it's an acid basically. They've not told you it's an acid though. It's a bit sneaky of them. HCl there, they've put the aqueous HCl. Essentially we're talking acid here. So it's going to react, and this is lysine. So in that situation it's going to react as a base, which means it's going to be a proton acceptor. And this is where the protons are going to be accepted. So I'll leave this up slightly because it's difficult otherwise. C, still going to remain. CH2, 4, H2N, and then, just copy it directly. I want here, H3N, and here, obviously, NH3 with a plus there. So it's accepted. Note that it accepts them on both. Don't just do the one, it's got to be both. Okay, both of those nitrogens. An excess of aqueous sodium hydroxide. The opposite's true here. So we're going to have the H2N, CH2, 4. It's going to act as an acid. So it always does the opposite. So it's going to donate the proton. Here we're just going to have the NH2 groups as per usual. So it's the acidic conditions, alkaline conditions, methanol in the presence of a small amount of concentrated sulfuric acid. So, okay, so it's going to, this one, I'll use this one as a reference. Obviously imagine that this is the carboxyl group. This is going to react as an ester. We've got alcohol, we've got the carboxyl group, which is going to therefore treat it almost as carboxylic acid. So we're going to have H2N, CH2, 4, CH, NH2, C, and that's obviously the small amount of this is our catalyst in this case. So we can hear people shouting, they're playing football. Noisy. COO, CH3, because it's methanol that's being added. So C double bond to the O to the O to the CH3. And that is our molecule finished. So 3 marks there for drawing the various bits. Don't be twicked out. That's the next word I'm going to say. Don't be tricked out and think they're going to do the whole Zwitter ion thing, because they won't necessarily do that. Okay, just bear in mind. Obviously, read the questions well. Bit of a naughty one that, dipping into sort of the carbonyl stuff and pulling out the idea that it's got this C double bond O H, so the carboxyl group. But at the same time, it's getting later in the paper. They're expecting a bit more of a higher demand now. Mass spectrum of alanine gives a major peak at MZ44. Write an equation for fragmentation of the molecular ion of alanine to give an ion that produces this peak. Right, so alanine is here. So it's a nice, easy one. So it's a standard, real basic lark there. So we've got CH3, we've got a C, NH2, we've got an H, and we've got COOH. Now, for a start, we've got to give it all this. That's our starting point, okay? It's a charged radical. It's going to break down into an ion and into a radical. Now, what is the ion going to be? That's my question. Okay, so what's going to happen here? We'll leave that for now. We're looking for something that has a peak of an MZ44. Now, what I would do here is I'd look at the MR of this total thing here. So the MR of my total group is going to be 15 from the methyl at the top, added to the 1, which is the hydrogen, added the C double bond O, which is 12, add 16, oh no, add 16, add, yeah, 15, 1, 12, 16, 16, add 1. God, this is a confusing calculator. 15, 1, 12, 16, 16, 1, add 14, add 2, add 12. It's going to give us 89 as our MR for this portion. So we need to lose 45. So this needs to have an MR of 44, our fragment here. I'll run through this in a second. So MR of 44. So we've got to lose 45. Always assume that there's going to be a single cleavage, which always gets a bit of a giggle, but there you go. So a single cut somewhere here that's going to, one part of it's going to come off. So this has an MR of 15, so that's not going to do it. This has an MR of 1, not going to do it. MR of 16, not going to do it. MR of 12, 32, 45. So that's our 45 portion there. So what we're going to end up with is we're essentially going to go bam, bam, CH3. That's going to where our charge is going to be. But I think you could probably do the charge overall with big square brackets, but it's going to be coming from there. What are we left over with? Our radical, which is the C double O H there. This has to be charged because it's giving us a peak. If it's not charged, it won't be deflected and it won't be detected. So it's got to be charged in order to actually meet those requirements. So charged, and then obviously the radical left over, 2 marks. Draw a dipeptide formed from 1 molecule of lysine and 1 molecule of alanine. So basically we're going to join them, and the join is going to take place through the OH group and the NH2 there. So we're ultimately going to end up with this. There's a few different options here depending on which one you want to put where, but I'll just draw it this way around. There's just an option that you could go for. See. So that's where I've joined the OH of the carboxyl group and the N there to the follow. This is where basically this is other amino acid. This is the other amino acid. So that's the separation point, if you like, down here. NH, C, CH3, H, COOH. And that's just one method that you could draw there. Okay, so last bit of this question then. It's like a fisherman's friend. Gosh, strip my tongue. Dipeptide in question 60 is hydrolyzed in acid conditions and the mixture produces analyzed. Blah, 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 blah. Right, so again, another suggest question. They do love a suggest question in this paper, so it's one of those where you're not necessarily going to know the answer from textbook learning. You've got to sort of use your chemistry brain to work it out. So the dipeptide we're talking about in here is hydrolyzed in acid conditions. Acid conditions means that it's going to act like a base, so we're going to find that it's going to accept protons and it's going to be charged. That's winding myself up now. It's right. Okay, so I think what we're going to find is that we're going to. Okay, sorry. Start again. Hydrolyzing this, we're going to break it down. We're going to split it back into its amino acids. Because it's acid conditions, it's then going to cause them to be charged. I would say. Looking at each one, 2 NH2 groups there, 1 there. This one's going to all 3 are going to become protonated, but this one molecule here, lysine, is going to have 2 protonated groups, whereas alanine is only going to have 1. So lysine leaves after alanine. Well, it kind of sort of, if you think about it, you've really got to sort of think about, well, what does that suggest? That suggests to me, obviously, that it's travelling through, obviously, more slowly. From column chromatography, I would say, therefore, lysine sticks better, English is terrible, to the stationary phase. Why though? Why is it going to stick better? 2 marks, and the reason for that, I would say, is going to be because it's more positive. More positive means that it has more ability to absorb onto the stationary phase. Therefore, it's going to travel through slower. It's ultimately going to leave, but it's going to travel through slower than alanine is going to. So, Now we're on to question 7, section B now, and we'll start straight off with some NMR spectroscopy. So we've got ester 1 and ester 2. One of the two esters produced this spectrum below. To deduce which of the two esters produced the spectrum below, in your answer, explain the position and splitting of the quartet peak at delta 4.1 ppm in the spectrum. Yada yada yada. So, got my insert here ready. So 4.1. So this is hydrogen. Check again. This is hydrogen NMR. I'm looking at 4.1. So looking at this guy here, 4.1. Bearing the kind of molecule we've got, is going to really, we're going to be looking at this portion here. So we're looking at something where we've got an R group, COO, and then the hydrogen in question is going to be on the next to the O. Okay, it's attached to the carbon, which is attached to the oxygen. So which of the two esters produce a spectrum below? So it's 4.1 is this bit here. So we're looking for something where, okay, yeah. So we've got an R group, O, and then it's these hydrogens here, or 3, depends on what it's going to be. Yet they've produced a splitting pattern of a quartet, which means adjacent to them must be this CH3 group. So it's got to be this ester here. This ester here, ester 1, must be the ester that's producing the spectrum that's seen. The reason being, really, I think it's a nice one to sort of use that 4.1 certainly to help you. Explain the position and splitting of the quartet peak. Well, explanation is due to it's this portion here causes 4.1 peak. Splitting, what's happening there? Well, the splitting is because it's a quartet because adjacent, so it's quartet because it's adjacent to CH3. Okay, predict the delta value of the quartet peak in the spectrum of the other ester. So the other ester is going to have the quartet because of this environment here. So next to the carbonyl group. Look on here. So we're looking at this one here, aren't we? It's got to be this guy here. So the range we're dealing with is going to be delta 2.1, 2.6, taken directly from the data sheet there. So that's question 7a done. Let's go on. Question 7b. Cetramide is used as an antiseptic. Name this type of compound. To give the reagent that must be added to blah blah blah. Right, okay. Let's start this one then. So name the type of compound. Well, straight away I've got this. I can see here that I've got a. Yeah, it's a quaternary. It's a quaternary ammonium salt, if you like. Yeah. Reason being, because the whole thing, obviously, this is the sort of quaternary amine, and it's the ammonium salt because it's obviously bound to we've got the bromide there as well. That's our central nitrogen. We've got 3 methyls and then this long portion here. So type of compound, it's a quaternary ammonium salt. Give the reagent that must be added to CH3, CH2, 15NH2 to make cetramide and state the reaction conditions. So we've got NH2, right, so we're trying to replace each of these H's with a CH3. So what we've got to add to that is basically, because we want to put a CH3 onto there, we've actually got to react it with bromomethane. And it's almost the opposite way around. This would act as a nucleophile attacking the carbon there, bonding it on, therefore leaving us with the CH3 added on. So it's bromomethane. If you don't understand that, you're easier to sort of actually to draw it out and to get grips of what's happening. But this is the actual nucleophile. This is nucleophiling, attacking the bromomethane once again. So it's going to do it once and replace one again. And then again, I believe that's going to take us to the, that's going to take us to the quaternary. amine. What we're looking for though, because we want to sort of basically saturate it, if you like, with the methyls here, we want this to be excess. Otherwise, we're not going to allow that. We're going to find all the intermediates are going to start reacting with each other, because that's the nature of sort of the nucleophilic substitutions, A2, the ones we look at. Because everything that's produced that's either a primary, secondary, or tertiary amine, all of those nucleophiles that can go on to react. So we really want to force it to react with the bromomethane, so we add excess by that reason. And the type of mechanism, straight from the AS, touched on A2 as well, nucleophilic substitution. So, go down, 7C, describe a reagent that could be used in a test tube reaction to distinguish between benzene and cyclohexene. Right, okay, nice one. So, we're looking at the difference between benzene and cyclohexene. Well, this has got a double bond, so straight away I'm going bromine water, benzene remains orange, and I'd go cyclohexene turns colourless, and to give the starting colour, colourless from orange. Nice one there, another 3 marks. 11 marks there, question C. We're on to question 8 now, so let's see where we go. This question about some isomers of C5H8O2. Compound H is a cyclic ester that can be prepared as shown. On the structure of H, 2 of the carbon atoms are labelled, A and B. Name and outline the mechanism for this reaction. Okay, this is a nice question. The reason being that it's very sort of application heavy, in that we're taking a single molecule and reacting it to form this this cyclic compound and then hydrogen chloride. It's essentially an alcohol reacting with a acyl chloride, but it's this sort of aliphatic molecule here, this straight chain. So all we've got to do is just twist it round. So do this. To something like that. OH here. So that's going to react with that. That's going to happen there. I'm not going to draw the rest of it. I'm just going to keep this part here because I'm quite lazy. I'm going to ignore the rest at this point, but it's just again the C, 2, 3, 4 with the hydrogens on there, blah blah blah. Okay, what happens now? That moves back onto there, reform the double bond. We get that ejection happening there, and then I've got the charge on here. That moves on to there. Yeah, hydrogen coming off. We've got a hydrogen chloride there. Boom, boom, boom. So that's the mechanism. Name the mechanism. This is nucleophilic addition, elimination. The reason we know that because we obviously added something we've eliminated, in this case the hydrogen chloride that's been spat out. So that's our mechanism done. Use table C on the data sheet to give the carbon 13 NMR delta value for the carbon atom labelled A and the one labelled B. So the one labelled A has got a carbonyl group next to it. So it's this one here we're looking at. So I'd probably say 20 to 50 for that one. So again, taken directly from the datasheet, and B is with an oxygen next to it. So probably we're going to look at this one here, 50 to 90. Yeah, nice. It's quite a straightforward one actually. 50 to 90, 7 marks there. A huge number of marks. So there you go. Mechanism done. Oh, still a bit more. Okay, HO, CH2, 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 COCl can also react to form polyester in a mechanism similar to that in question 8AI. Draw the repeating unit of the polyester and name the type of polymerization involved. So straight away, I know because there's only two types of polymerization. We've already looked at addition. It's going to be condensation, polymerization. What are we going to produce? So the trailing unit, the repeating unit that's going to be present in our polymer. Let's have a think. So essentially what's happening here, the repeating unit is going to be formed as a result of this guy reacting with itself pretty much. So what's going to end up with, because we're forming a polyester, we're going to end up with ester linkage, which is that. And one of the ways I think it's always useful to do this is that you need to end the molecule so that it could form that if it reacted with itself is always, I think, a nice way to sort of deal with this. So drop the Cl, drop the H, that's the easiest thing. So we go O, CH2, 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 CO, trailing bond, CH2. Now, if this reacted with itself, we would get that correct ester linkage, which is a good check to make sure you've done it right. I think sometimes certainly in the past, I used to find it a little bit sort of confusing as to sort of what to put where. This is absolutely fine. You've got your trailing bonds, and you've got the correct point, which is basically this, but polymerized. State how you could distinguish between compounds J and K by a simple test tube reaction. So, it's come from nowhere. J and K, so... Okay, so this is, it's got an aldehyde group. This one's it's a diketone. And this one's like a ketoaldehyde, but even still has the aldehyde group there. Standard answer, I'm going to go Tollens. J and K, I'm going to go K. Silver mirror. J, no visible change. Or if you like, no reaction. But then state how you can distinguish J and K by giving the number of peaks in the NMR. Oh, sorry. Yeah, simple test tube reaction, yeah. State how you can distinguish J and K by giving the number of peaks in the hydrogen NMR spectrum of each compound. So, hydrogen NMR, 2 peaks. This one's going to be the same peak because it's a symmetrical molecule. This one's going to be on its own. This one here, that's going to be 1 peak. That's going to be another, that's going to be another, that's going to be another. Look for symmetry in molecules. If there's symmetry, you're going to find that there's going to be shared hydrogen environments at different ends of the molecule. There's not symmetry, they're all going to be different. So basically this one's 2 and this one's 4, but obviously written in this base here. Another 5 marks there. 8 continues, we're almost getting there now. Okay, draw the structure of each of the following isomers of C5H8O2. Label each structure as you draw the correct letter L, M, N, P, or Q. So L is methyl 2-methyl propanoate. Oh, nice. So L. Let's start. I like to do it this way around. So propanoate. Okay, so it's going to have the double bond there because you can't have the double bond here because it's too many bonds. Methyl 2-methyl, so it's got to have a CH through group there. 2, 3, 4, 1, 2, 3, 4. Methyl 2-methyl, methyl CH3. C5H8O2, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. Lovely. We're not required to do display, so I can do the condensed version there and O2, so that's fine. So that's L done. M. M is an ester that shows EZ stereoisomerism. Okay, ester that shows EZ stereoisomerism. So, let's have a look. I would base it around that. We know we've got to have different groups here, so I can't have 2 hydrogens on this side because it's not going to be EZ. It's got to be an ester. Something like 1, 2, 3, 4, 5, 2, 3, 4, 5, 6, 7, 8. Yep, that fits fine. It's really sort of about trying to just work it out, try and get the best sort of you can here. It's going to take a bit of time, but it's really got to sort of just do your best. N is a carboxylic acid with a branched carbon chain that does not show stereoisomerism. So not EZ now, we're talking about stereoisomerism, so we're looking for it. Basically, we've got to look for carbons having multiple groups, the same groups attached. Is always a good way to sort of do that. So N, or certainly, obviously, one that doesn't show EZ, so one that's got the same stuff on this on each side. So this one, for example, we could do, yeah, quite easy actually. We just switch that and that. So H. Boom. Switch those and that. Finished. N. P is an optically active carboxylic acid. So P. Optically active. We've got to stick with this C, this double bond, because of the number of carbons that we've got. Excuse me. Now, carbon needs to have the correct number of bonds. Okay, so yeah, you could put 4 down here. That's not very well written, but that thing there. Q. Cyclic compound that contains a ketone group and has 2 peaks in its NMR spectrum. Straight away I'm thinking, so it's got 5 things, 5 carbons, so ketone, 2, 3, 4, 5. Would that work? No, we've got an oxygen. Well, you haven't. I've got an oxygen. Yeah, 2 peaks. 1 peak, 2 peak, obviously with the hydrogens in there. Whew. It's a tough last question. There's a lot of work there, a lot of effort actually for 5 marks. But it's at the very end, so you'd expect that. That is the Unit 4 paper, an hour and 15-ish minutes. Hope that's been of some use. It has been fairly quick, and I apologise for that. But slow me down, pause, rewind, all the rest. Ask any questions, any problems that you've got. And again, yeah, hope that's been of some help to you.